In this example, we're going to cover inverse kinematics of a two-link manipulator. So inverse kinematics is where when we are given the tip position or end effector position, we find the joint angles. So in this case, we are given the tip position x, y, and we need to find joint angles theta 1 and theta 2. So theta 1 here is the angle between link 1 and the ground. We'll label that theta 1. And then link 2, or theta 2, is the angle between link 2 and link 1. So here would be theta 1 still. We're going to be able to get theta 2 first. We'll do that using the Pythagorean theorem and the law of cosines. And then we'll use more trig to get theta 1. So we'll write our plan down here. The first thing we can do is find the displacement of the tip. So the tip is here, and if we draw a line from the origin to the tip, we call that R. We know that R is going to be, using right triangles, R is going to be x squared plus y squared. So we have x here, we have y here. R equals x squared plus y squared. R squared equals x squared plus y squared. And then also so that's using Pythagorean theorem. So now using law of cosines, then we will have R squared equals L1 squared plus L2 squared plus 2 L1 L2 cosine theta 2. Okay, so that would be using this L1, that L2, and then the theta 2 angle. We have the plus here because we know this is going to be greater than a right angle. Now we can just totally get rid of the R squared and just equate the x squared to y squared, the law of cosine stuff, and then solve out for theta 2. So let's rearrange this now. We will have x squared plus y squared minus L1 squared minus L2 squared over 2L1 L2 equals cosine of theta 2. So we could just use inverse cosine and solve for theta 2, but that wouldn't get us quadrant specific. So if we want to get quadrant specific, we have to use tangent, because tangent includes the sine and the cosine, and sine and cosine each are only defined over 2 quadrants. So to get the whole 4-quadrant position, you need to use tangent. Now on an exam, either one would be okay, but we want to do it the most accurate way possible. So we can relate sine and cosine using tangent, and also using the trig identity. We know that sine squared plus cosine squared equals 1, and sine over cosine equals tangent. Okay, so we have cosine here. We can use this first trig identity to solve for sine, and then we can plug both of those in and get tangent. So we'll just say that cosine of theta 2 equals star. Call that star, so we know that sine equals 1 minus cosine squared square rooted. So sine equals square root of 1 minus star squared. And so plugging those both into there, then we'll get square root of 1 minus star squared over star equals tangent theta 2. Okay, so we can do inverse tangent of that and solve out for theta 2, but we need to actually plug some numbers in here. So if we take all the numbers that are in here, then we will have the 0.981. So now we'll take that 0.981 and we'll put it all into this stuff, and we'll get theta 2 equals tan inverse of square root 1 minus 0.981 squared over 0.981 0.195 radians, or 11.2 degrees, equals theta 2. Okay, so that's theta 2. So now we need to solve for theta 1. So looking at this, we have theta 1 is that angle. Now, using the law of right triangles, we can find that angle. We'll call that beta. And then the angle between R and L1, we'll call that gamma. So from there, we know that theta 1 plus gamma equals beta. Okay, so we can first find beta using that big triangle with X, Y, and R. Then we can find gamma using a different triangle, and I'll get a different color for this. So we have R here, and then if we extend theta 1, or extend L1 in that direction, so that we get a right angle here, then we have another triangle. So I'll draw this again down here. We've got R, then we've got that triangle, which basically is L1, L1, L2 here, and that's the right angle. And then finally we've got down here theta 1, and then this one is theta 2. Okay, so that green triangle basically is what we're going to solve for to get gamma. Okay, and then beta is both of those together. So let's find beta first. So we know that, so this point was xy. So beta is just going to be the inverse tangent of that. So beta equals tan inverse of y over x. So beta is 0.894 radians. So now gamma, to get gamma, we're going to do that green-red triangle. So the gamma angle is going to be in the inverse tangent of those two green sides. So gamma equals tan inverse of the opposite side, which here would be L2 sine theta 2, over the adjacent side, which is L1 plus L2 C2. And that comes out to be 0.13 radians. Okay, so now finally, to get theta 1, we just subtract. Theta 1 equals beta minus gamma. 0.894 minus 0.13 equals 0.764 radians. And if we convert that to degrees, we go times pi over 180, and that is 43.8 degrees, theta 1. All right, so basically what we did here is we took the two-link manipulator and we broke it into pretty much all the triangles we could find. So we used the Pythagorean theorem and law of cosines to get theta 2. And then we did some more trig, more Pythagorean theorem to get theta 1.